Welcome back to the video lectures of MLIP course. We are in the third lecture in the Bayesian classifier module. In the last class, or maybe in the first class of this, we have figured out it is indeed what we would be finding out in this whole process are the a posteriori probabilities for a given x bar. All you need to do there is from that compute probability of that omega I belong given x bar. This you compute it for all classes. Let's say there are m classes, and eventually you assign that x bar to a class that has maximum probability. So assign x bar to that class which has with that class which has maximum a posteriori probability. Okay, this was the kind of take home message from the first class of this module. In the second class, that's the class yesterday, we worked out how to compute these a posteriori probabilities, right? So then we, let's say for this, we made use of the Bayes theorem. And let's say, what is this equal to? Probability of omega I given x bar is equivalent to, can you tell me the expression? This is equivalent to probability of x bar given omega I into probability of omega I divided by probability of x bar, right? And what is P of x bar? Probability density function of x bar simply. What is P of Wi referred to as?
Prior probability.
Right, prior probability of class I, prior probability, correct? And what about this? P of x bar given omega I is referred to as?
Likelihood.
Yeah, that's the likelihood of x bar with respect to omega I. Then what you do, you are going to compute it for various values of I, that is various classes, and pick that one which has a maximum value. We also discussed how you could compute P of x bar, how you could, I mean, those are particularly for likelihood and prior probability, some ways of computing we have done. Those are not the only ways to compute, but we have discussed how to compute them, right? How to model them rather from a given training data set. And now we further made some assumptions and looked at few more inferences, made some more inferences from that. For example, one such special case we considered is assume you have two classes, and then your P of omega 1 equal to P of omega 2 equal to 1 by 2. Then assignment of classes was such that if probably for a given x bar, if probability of, because then for both classes these two are fixed only, then based on likelihood directly relates with the a posteriori probabilities. So in that case what we did is, if x bar given omega 1 is greater than probability of x bar given omega 2, then if that is the case, you assign x bar to which class? Assign x bar to
Omega 1.
omega 1. Very good. Else you assign it to omega 2, right? That is what we discussed in the previous class. And then we have also plotted some, assuming that these distributions are, let's say, Gaussian. Assume that this is one distribution. Say here on your x-axis. I'm just plotting one line, means this is with L equal to 1. It's a unidimensional. Your feature vector has just one component. Here I am plotting my likelihood function, which is x bar given omega I. Then there are two classes. Assume that that's one class and this is another class. So this is, let's say, probability of x bar given omega 1, probability of x bar given omega 2. Correct? So look at the statements that we obtained here. X till what point on this x bar given omega 1 is greater than x bar given omega 2. This is quite obvious, that too when your variances are same there. We'll come to that what it means exactly a little later in the next classes, but for now, from the drawing, this could be the region R1 where you assign, if your x bar is within the region R1, you assign it to class 1, or else for the rest of the region, you assign it to class 2, right? So till here we have done in the previous class. So let me now calculate something called as decision error. Decision error. How much error could be there in these decisions I make? You could notice here from this graph that in this kind of allocation, when your value, let's call this as x naught here, any x bar with the threshold of x naught, any value less than x naught, if you are assigning it to class 1, you could notice still there, it means that's the best thing you could do, but here there are few samples that would be wrongly assigned to the class 1, which should have been ideally should have been assigned to class 2. But you could see here, let's say in this region, if you look at till here, if you look at, these are the possible, means this is on the other hand, the probabilities of occurrences are like this there. If you had, on the other hand, if you, that's the best thing you can do, because the error is minimized there by assigning any feature vector less than x naught, or which is there in the region R1, I would call, because less than x naught will not hold good as I am scaling up to more number of classes. Then what comes into picture is in fact the region, okay, within that region. So I would be using the region R1, I would call it. Okay, so there is some error, but can we quantify that error? Let us start with a simple case. Gradually we scale up to generalizing it. So for now, let's assume your probability, prior probabilities are same. P of omega 1 is equal to P of omega 2. And of course, then it has to be 1 by 2. Then if I see how much error I committed, first of all, how much error or misclassifications happened for class 1. If you look at the class 1 is, the errors are committed over the region R2 there, right? And if I take the area now in the R2 for this likelihood function of class 1, the one which I marked there in red will give me that region. It is in this region, there is an error. So area under the region R2 by the first curve would give me the error contributed there, which would be like, what should I write there now? That's nothing but probability of x bar given omega 1. Okay, and the probability of occurrences of half of them would occur in this. So when I'm considering the average error, I would put here half. I'm not doing any rigorous proof here. I will do a rigorous proof a little after that. I want to make sure that first you would get some intuition for this. Okay. And of course, you want to compute area under this curve for which is your variable here. What is the
dx.
variable? Right, dx bar. Okay, since here you could have kept x also because there is only one. Okay, just by a similar argument. Now I would see which should be ideally in class 2, but that has been misclassified. If you look at it that way, maybe I would just see here. Let me put with this color. Anything after x naught, I am assigning it to class 2. But when I put x naught here, there is an error going on here, which I have drawn in green there. Can you tell me the expression for that now? Plus, what is the error there? Can you tell me the expression there for this? The decision error or probability of error, let me call it PE. Okay, what is that value now?
Sir, half into
Half into
integration over
over.
R1,
Very good.
R1,
Ah,
probability of x bar given omega 2 dx.
very good. Good. This is the probability of making a decision error. Now, suppose let me just write it, the expression for any, if you want to write this for any values of prior probabilities, all this would become is, just a minute. Yeah, then this expression would become, of course, then, well, this omega, this is one way I would tell you, to give you an intuition. The way I would tell you is that, yeah, well, this is what you want to look at, but it has so happened that you are looking into the likelihood function because these were same. If not the same, the likelihood function with respect to which class you are doing, you will be multiplying it with that particular class. So this would become then probability of omega 1 into integral over R2, probability of x bar given omega 1 dx bar plus probability of omega 2 into integral over R1, probability of x bar given omega 2 into dx bar. Anyway, omega 2 probability has nothing to do with that x bar. So I just took it out of the integration. It's a constant value, which could vary depending on your particular problem. This is the decision error that you are bound to make here with this type of classification. So now I'll tell you first one practical scenario where you may want, you are okay with performing some misclassification with a particular class, but not as much as you are okay with one particular class, you are not okay with another class. So maybe let me give you one practical example. Let's say I have two classes, omega 1 and omega 2. Assume that this omega 1 corresponds to a class of malignant tumor. Okay, this is one scenario I'm telling you. Otherwise, whatever I do later, all the math looks pretty dry. There is a motivation for doing this. So I'm giving you one practical example here. Let this represent the class of a malignant tumor. Similarly, let omega 2 represent a class of benign tumor. I guess you know already by this time what it means by malignant tumor. It is something that has the potential to spread. So that's where you need to either give a radiotherapy or take some action there. There is a tumor, but when this is a benign tumor, it's not dangerous. That's altogether a different kind of treatment or action would be required here, which is not as severe as malignant tumor. Typically, what is done is, for example, if somebody, the quite common one in tumors, one of the prevalent ones is, for example, breast cancer. So somebody has found or felt that there is a tumor in the breast, then they go to the hospital. Then there is something called as mammography. Mammography. This mammography is more of a screening test. See, for example, there are 1,000 students appearing for an IIT exam. You cannot scrutinize each and everybody in detail. 1,000 students for, let's say, 10 positions available for 10 students that you could take. So what you will do is you will bring from 1,000 to 100. You screen them, and on these 100 people, you would do a detailed test. Let's say all I need is 10 students. There is a one very good student, okay, who from the screening test, here it is okay if there is a below average student, he is passing through the screening and coming to the next level, because here you are going to do a very detailed test here, but not the other way around. Your screening test should not be a very tough test, okay, where for some reason in the particular topics that you are testing, it has to be generic. If it is very specific, you might miss a very good student coming out of, may not come out of this, and by the time you do a detailed test, that time itself he is out of your evaluation. So similarly, when we say mammography is a screening test, if it comes positive, positive and negative now, thanks to COVID, if he comes positive, if she comes positive in mammographic test, it is not a confirmation that she has a malignant tumor. It only that then you go for a biopsy. Biopsy means they take a tissue out of the suspected lesion or a tumor. They send it to a lab. They will analyze the biological tissue in that, and that's a kind of confirming test. So why is this so important to me? Because you are at the end doing this classification and telling to which class it is belonging to. Now, in the light of what we discussed so far, do you have any suggestions on, or do you have at least some thoughts on, is it the best thing to do, or do you think there should be something else we should do as an engineer when you are designing a classifier? Listen to me carefully. So now the way you could do classification here is you minimize this error, where if something belongs to class 1, let's call this as malignant tumor here, this as a benign tumor. What does the current one do? For example, if these are all the potential cases where they can be still malignant tumor, but because they are greater than x naught, you would right now put it into the benign tumor. But the additional information I'm telling you now is that I'm okay even if some benign tumors are wrongly classified as malignant tumors, because anyway this is not a final what do you call, it's not a final judgment, it's not the judgment day for you. You go to the biopsy after this. So if a benign tumor is misclassified as a malignant tumor, it is okay, but a malignant tumor should never be misclassified as a benign tumor. So do you think it would require, do you think still this purpose will be served by minimizing this decision error, which is, or decision probabilities, or do you think something else should come here? I want to minimize some error function. Right now, my decision error function is like this. What do you think should be done to this to achieve the aforementioned objective?
We can shift the value of x naught towards right, sir,
Hmm.
and
Towards
right
right.
towards omega 2.
Correct. That's a good
And
point. What we should
okay,
have done is we should have moved it to somewhere here. Correct. Then, of course, it cannot be 0, but now you are giving a more leverage, 99%. Okay, nothing, no test can be 100%. Keep that in mind. or you might still move it till here also, this case also. Okay, till here you could move it to the right. Very good. Now I want you to translate this idea into this equation, because at the end of the day, you are the one, you are going to design the classifier, and it is the based on that algorithm you are going to get your results. So how do you think this decision, this error right now, without having any such bias and simply looking at it, if I am going to, or even you could look at it here, if I am going to minimize the probability errors, I would be getting the classifications. But now I want to take this, put this additional constraint here. How do you think this can be achieved? Any ideas on that? This, with some modifications, you should be able to achieve this. So how can you do that? Any thoughts about that? So maybe let me redefine my question, rephrase my question. If I minimize this equation, what would be the X bar value I would be getting here? What would be the X bar value that minimizes this equation? That will be the intersection point of these two things, correct? That's what would eventually minimize this. Now, minimization, I need to modify that equation such that my minimization would give me a line which is right to the X naught in the particular, in this current case. Later, I'll make it to generalize it so that class 2 could be malignant. Then I should move it to the left. Okay, this I should, what is it? I need to introduce something into this equation such that minimizing it would give me the decision boundary. See, my question is this one. Now, minimize, now you introduce some more parameters into this equation such that then minimizing that particular equation would now give me a new line or a decision boundary other than from X naught. Currently, if you solve it, it will give you X naught. This is called as minimizing the average risk. What will be done here is you put a different penalty. See what it is giving you. This first term is giving you the penalty. I can call it penalty also, right? First term here is giving you the penalty for misclassifying a feature vector into class 2, which should have been actually class 1. Is my statement clear? The first term here is giving you the penalty that will be applied when you are misclassifying a feature vector from W1 to W2. Is that not all that is happening here? This is the penalty. You see that one which has been written in red. That is nothing but a penalty that has been imposed when you are giving an X bar. You are assigning to falsely assigning a falsely assigning a feature vector X bar to omega 2, which should have been to omega 1. And similar lines, the second one is giving you the penalty that you would be this. You look at this one, this term. This is giving you the penalty that you are imposing for assigning a feature vector wrongly to class omega 1, which should have been assigned ideally to omega 2. Till here, are my statements clear or not? Are you able to see that interpretation here or not?
Sir, I think the second statement, you said it the other way around.
Oh, is it? Okay. So let me again then restate that. See, when you look at this part is the first term, okay, where this should have been assigned to omega 1, but you have assigned to omega 2. That is the first term here. Probability of X bar given omega 1 dx bar for region R2. And for this region, this which I am showing now, let's say in green here or red here, red circle, that I have assigned to omega 1, but that those fractions should have been assigned to omega 2. That is what has been there in the second term. That is the penalty coming because of that. Is that clear?
Yes, sir.
Good. Now what I want to do, for misclassification that occurs for the class 1, I want to increase the penalty. It's very simple. All I need to do now is, let me call this with a variable or risk, minimizing the average risk. I'm calling it. So let me call it as R. For misclassification of 1 into 2, let me put the penalty as lambda 1, 2 here. Then of course there is a probability of omega 1 integral over R2, probability of x bar given omega 1 dx bar. And similarly, I am having a different penalty here for misclassification of a second class to the first class, which I am indicating by lambda subscript 2 1 into probability of omega 2 integral over R1, probability of x bar given omega 2 dx bar. Now, in the current case, in the case of, let's say omega 1 is malignant, okay, and omega 2 is benign, which one among lambda 1, 2 and lambda 2, 1 should be high? Which penalty should be high? See, if at all something that is belonging to omega 1, malignant tumor, has been wrongly assigned to omega 2, this is the error I am getting. This I want to penalize more. So lambda 1, 2 will be greater than lambda 2, 1. Are you all
Okay, yeah,
guys?
penalize more, but that area will be reduced.
Correct, correct. Area will be reduced. But penalize, this would happen when I choose lambda 1, 2 greater than lambda 2, 1. If omega 1 is benign tumor and omega 2 is malignant tumor, then lambda 2, 1 should be greater than lambda 1, 2. See, finally, a given x bar, think about it in this direction. Why are we doing all this? We started with a simpleton case where I just have two classes and I treat them equally. Things are simple. And even I considered prior probabilities are same. I simply look at what are their likelihoods. And for a given x bar, whichever likelihood is more, I choose that. But well, one more layer we have brought. Well, I cannot treat misclassifications from any class from class A to class B for any AB values. I cannot treat them in the same manner. So I introduced this. But still, so far, there are only two classes. But in practice, you could have more classes. So that we have to do, more classes we have to consider. And at the end of the day, when you have more classes, you have different penalties for transgressing from one class to the other should be there. Still, you should be able to then come up with an expression that tells you to which class a given feature vector belongs. Unless you have that way of computing it, this is of no use. So that is our final, at least for now, that is our final goal to reach. And we are gradually building up things, gradually generalizing things and moving there. Okay. If this is not clear, it won't be, you won't find it like convincing and why we are complexing, making things complex. Okay. With that, now let's go to, let us first generalize to m number of classes. I have generalized, if you notice, I have introduced the prayer probabilities already. I have introduced the penalties. One thing still I haven't done is generalizing it to m number of classes. Okay. Now let m be any number of classes. So this is what the next step we are going to do. Now, the risk or penalty associated, let R subscript I represent the penalty associated with class I. Let us first calculate that. How much would be this penalty? Please work out along with me and please do give your full attention here. Otherwise, later you will find it quite time consuming and complicated. Now, what it means is, suppose a feature vector belongs to a class 1. That is what, and then it has been wrongly assigned to any other class other than this. How much penalty, or what are the penalty terms associated with this? So class wise, I am computing it right now. So for ith class, I am calling it as R subscript I. For right time being, I would also put a term penalty for delta ij is there. There will be one value of j for which j equal to I. What should be the penalty? So as I said, when I say lambda 1, 2 is the penalty is the weighting term associated with misclassification of a feature vector, which should have been in class 1 but has been assigned to class 2. So with the same definition, what should be delta II for any value of I? Delta II is penalty associated with assigning a feature vector that belongs to class I, and you also assigned it to class I. So then how much penalty should you do for
1
such
minus
classification?
1 minus delta ij.
Very good. Okay, you are telling it for delta ij. Yeah, very good. Or if it is, they both are same, this is simply 0. Delta ii is 0, right? But for the time being, for the sake of writing them later in matrix form, I would keep still delta ii wherever it comes, but keep in mind that in practice you make it to 0. Okay, that you will understand later. Fine. So ri, what I would do now, penalty associated with that is, or maybe let me call it as RK here. Maybe I'll use the same things that are there in the textbook so that there won't be any confusion later when you try to match it with this. So I use the same subscripts there. So this, let me call it as, for the kth class RK, this is called as, so probability of omega k into, there are m classes, I equal to 1 to m lambda ki. Okay, I'll just erase this here. You have already noted that, I guess. Into integral over Ri, probability of x bar given omega k into dx bar. Okay, let us spend some time with this equation now. The feature vector belongs to a kth class, right? Now, in the regions, well, don't worry about I becoming k, then I would make this to be 0. Okay, lambda kk will become 0. So don't worry about that. Just look at all other regions other than rk. Then what you are doing, so the fraction of feature vectors that would have belonged to this class is in this region. You would see how much is their probability of x bar given omega k in this region. So just look at here, the earlier curve, and then your interpretation will become clear. So this probability of x bar given omega 1, you are doing it in R2. If there is something else, another class is there here. Okay, then what we'll do, probability of x bar given omega 1, you would do it in, let's say there is some more cutoff here, you will do it in R3 here. In the same manners, you are doing it for all regions, and you are putting an penalty term, you are varying it. How much can you allow for a misclassification from kth class to the ith class? This I varying from 1 to m.
Sir, after one class, it will become 0 because one will not get misclassified into 3.
Which one?
If
One.
that graph which you have drawn, sir, in
Yeah,
that
yeah.
case,
Well, See, there what I did is there is just I have, you could consider maybe if you want, yeah, this it might become, but assume I have, okay. For that particular plot I have done, assume that my graph is like this, okay. Then that is something different. My mean and variance could be in
Yes,
any
yes.
way.
For this graph is
That is
okay. For this
possible.
one,
Correct, correct. For that particular plot I have done, it will be almost zero because after 99% it is there the way I have drawn it. But there is a possibility, isn't it?
yes, it is.
Good. So again, look at it that I am writing it for every class. So for example, you should also consider this class. So there is some error here done, there is some error here done also, right? So all things should be there.
Sir, what is R1 and R2, sir? Is it from 0 to infinity or?
It can be anything. See, well, that's a good question. For simplicity, here to plot things, I have considered x bar as a unit vector. So that, so R1, you could consider, at least in this example, for example, whatever I have drawn here, my R1 is from minus infinity to x naught. And my R2 is from x naught to infinity here. Now consider a case where I have this x bar is not just one thing, it's a feature vector. So it's there in L dimensional space now. Your R1 that time would be a region within that. So that would depend on, for example, in x direction minus infinity to x naught, y direction minus infinity to y naught, z direction, you go on and on. So this is a kind of a crisp one, but since x bar is there, that would be depending on how many dimensions of x bar are there, that region will have so many integrals there. Is that clear? It is just one region. Consider a 2D case, for example, or a 3D case, that will be a cube, it's not a cube, it would be one region there. Is that answering your question?
Yes, sir. Yes, sir.
Good. Then what we would do here is, what would be the total average risk? So this is the average risk we have written. So total risk or total penalty or risk here would be summation of, I should vary k value now, k equal to 1 to m or k. I should put it. Is it not? This is, see, the above term is giving from one class to any other class we are doing. This exercise we have to do for all m classes. Okay. By the way, I made a small change compared to the textbook. They have written this term separately in the textbook, where RK while defining, they did not keep it, but I felt this is better. So that's the only modification to the Theodos's textbook. Okay. Other than that, rest of the things I'm religiously following what has been given in Theodosius. Okay, so now it would be k is varying from 1 to m. I will substitute that here. Probability of omega k. And then I have one more summation from 1 to m, lambda ki integral over ri, probability over x bar given omega k dx bar. That's the expression for my total penalty. Now, what I would like to do here is, I would like to write this in terms of the regions. Okay. In terms of R1 region, R2 region, class 1 corresponds to R1 region finally. Class 2 corresponds to R2 region. That's what I would like to do. So this is a linear summation if you notice it. So I could bring, in fact, I equal to 1 to m here. Integral over ri is just depends on I, nothing to do with k. Within that, then I would keep summation k equal to 1 to m, then probability of omega k, lambda ki, or let me, lambda ki is more like a weight you are giving. So let me write it up before that. Probability also looks good. Other than that, there is no issue. Into probability of omega k into probability of x bar given omega k. Okay, this is the whole summation here. And this with respect to x bar here, I would do this. Just I interchanged the summations. Just the order in which this has been done is modified. Are you with me so far? Is that clear? So now, what is the final goal here is that you want to find out these regions in such a way that this penalty is minimized, is it not? So you have integral over each region. So that means each integral has to be minimalized. Each integral has to be minimized here. To minimize this. That means what I would do now is I am given an x bar. I need to assign it to one of these classes. Now, I would look at assigning this x bar to which region would minimize this risk. This is what I would be taking a look at. So how could I write that? So select the partitioning such that let us call it as Li. By that I mean you compute here k equal to 1 to m. Okay, k equal to 1 to m. See, this integration is done with respect to x bar. Given an x bar, let's say k equal to 1 to m lambda ki probability of omega k probability of x bar given omega k. Okay, and ulj, so this li should be less than lj, where lj is nothing but k equal to, let me just finish the mathematical write up here, then I would explain that. Lambda kj into probability of omega k into probability of x bar given omega k. See here what I for all j that is not equal to ki. So this is a very similar expression to what I have been writing earlier in the previous class. What it is telling you is, just pay your attention here. This is a slightly tricky part. You assign x bar, you look at by assigning x bar. So these are all the penalty terms you have. To which class, if you are assigning, this penalty is minimum. So because this finally this R has to be minimum. Okay. So what I am writing here is, suppose you are assigning it to an ith class here, then what will be the penalty here? K equal to 1 to m lambda ki, right? Probability of omega k into probability of x bar given omega k for that x bar value. Now, if you assign it to any other class other than this I, the all other classes you are indicating by j. J can take all values from 1 to m except I. And this choose an I such that Li is less than Lj. So to put it in simple terms, you compute this this expression, that summation, or whichever, yeah, that summation, assuming each value of I, and select that value of I for which it is minimum. As simple as that. It is just that mathematically, in a appropriate manner, I'm writing it saying that Li and Lj, this Lj can take all values other than I from 1 to m, and Li, if Li equal is less than Lj, then assign it to the ith class. That's all I'm saying. See, we have defined this penalty terms such that with the desired kind of assignment of classes, this penalty will be minimum. Minimum penalty will result in the desired boundaries. So far clear? That's why we have put there lambda 1, 2, lambda 2, 1. We will choose it this way. Then it would move to the right, for example, when this malignant tumor is there. So you are essentially, you want to minimize this R. Is that clear till that point?
Yes, sir.
Very good.
Yes, sir.
Oh, please do not hesitate to stop me if you don't. I don't feel bad if you say you did not understand. Rather, I would feel happy so that I will see in what other way can I explain that. Okay. Then now I need to see which assignment would result in minimizing this R value. That is all I need to find out here. How am I finding that here? Now, this whole, first I have written first the expression for this whole penalty term, which is containing all the terms that tells that I have 3 classes. What is the penalty of misclassifying something from which should have been in first class but has been given to second class, which should have been in first class but has been given to third class, which should have been in second class but has been given to first class, second but given to third, third but given to one, third but given to 2. These are all the terms I have written. So for example, 1 to 2, 1 to 3 are there in RK, each one. And then 2 to 1, R1 is that which tells us 2 to 1, 2 to 3 is there in R2, 3 to 1, 3 to 2 is there in R3. I need to sum up everything now. So that's why I have here K equal to 1 to M RK. And that has given me this equation. Is that clear so far?
In this
Yes, sir.
also, each class has only one attribute, sir, or it has multiple attributes?
What do you mean by attribute?
Sir, that we said no earlier that class has only one, uh, like one value which we are considering.
What is that one value? I'm not very clear.
Feature, sir. Does that
No. It has nothing to do with feature. See, if there are this x bar is a vector, all what would happen is here it will the region which you are looking will have multiple integrals. So integral over RA, which I have written. For example, you have 3 features. It will be integral over x, y, z. That's all. It is general there. It's just that within that region, you look at this region could be a one-dimensional one or for multi-dimensional one.
So there are M features, sir.
There are L features. No, M is number of classes. Don't confuse between classes and features. See, you have a malignant tumor and a benign tumor. These are 2 classes. This is M equal to 2. To do this, for example, I might be looking at the intensity value there, the gradient value there, some texture information there, something else there. So I'm looking at, for example, 4 components. Now, this corresponds to a feature vector with L equal to 4. M is different, L is different. Feature vector is different, M is different. Is that clear?
Sir, it is clear, but could you explain in the final equation where have we captured these features?
Yeah. See, feature is X bar I am writing here. And the classes is captured here, K equal to 1 to M. And these regions, when I say, yeah, that's all. So each class has one region. In which dimensionality is this region is captured by this X bar, this integral over X bar.
I am not clear, sir. Request if in the next class, could you give us a small numerical to work out so that this, instead of alphabets, it becomes numbers, it becomes more clear, sir.
That we will do anyway for sure. But even now, without that, it has to be clear. See, in how my region could be, for example, when my feature here is, pay your attention. If your feature is 1, you would integrate over X. For example, I have 2 features, then my region is actually it could be a 2D region. So it's like a box. Number of classes would come here. These which I have plotted here, the Gaussians are classes. this X bar is one feature. If it is 2, I would have then I would have it in 2D. That would give me the region is box. So that's where you would work it out in integral over R. Somewhat clear?
Yes, sir.
Okay. I will anyway give you some numerical also. Okay. Right. So coming back, is this equation clear? Now, I just mentioned that from each class to any other class making errors. From class 1, each K is giving you one class 1 to any other class, then class 2 to any other class. All of them you have written there, and that has given you this equation. Then all I did is, instead of writing it a class-wise thing, I slightly modified such that your equation, you are looking at the penalties region-wise. In this particular region, Ri means actually in this region, instead of assign this, what is the class error coming from 2 to 1, 3 to 1, everything in a particular region-wise I have written. Now, it is this function. So since this is again a summation here, each individual, for each value of I, this has to be minimum. See, when you are doing integral, this is area under the curve. This is a positive value or a non-negative value. It can be 0 also. Then, so to be more precise, it has to be non-negative value. Now, for this summation to be minimum, inside which there is an integral over each region, such m regions, each region telling you one class, each of these components have to be minimum. So that is how you would choose to X bar to assign it to which class. All you do is, suppose if I have given this X bar to a particular class, what is the penalty that I am getting? So you calculate all possible penalties here, and that which gives you a minimum penalty, to that you will assign it. Now, here the assumption here is, you know already the RA value here. We are not finding out the regions, rather given a set of regions, to which region or to which class a given feature vector should be assigned to. That is what we are computing. Since it's inside summation, that which gives you a minimum value, to that class you will assign it.